This lecture is a little outside the mainstream of our treatment, but it is important because most of the images we deal with visually have had their contrasts enhanced in order to improve their visual quality and range of colours. Here we want to understand a little of how that is done. The detectors used to record each band of image data are calibrated so that they can respond to the darkest and brightest cover types anticipated. Typically, those cover types could be deep, clear water or snow and cloud tops. That means that most of the cover types that are imaged fall in a range of brightnesses well inside the range from total black to full white, as shown on this slide. For a typical recorded image, the appearance is therefore slightly dull and poor in contrast. It would be good if we could expand the range of recorded brightness so that the signal of interest covers the full range from black to white. What we need to do now is understand how that can be made to occur. In order to set up a process for changing the range of brightness values, we need first some means for describing the distribution of brightness in an image or a band. We choose for that the image histogram, which is a bar graph of the number of pixels of a given brightness plotted as a function of that brightness value. Here we see an image as it has been recorded by an aircraft scanner. Note how poor it is in contrast, brightness and colour. Note particularly that it has a reddish appearance, as we mentioned in the last lecture. On the right-hand side, we have shown 3 histograms, one corresponding to each band, and coloured according to the colour in which the band is displayed in the colour composite image. Note that while each histogram commences close to the lowest brightness value in each case, that is 0, the upper extremities of the histograms are well short of the maximum available brightness of 255. Ideally, we would like the histograms to cover the full range of brightness. If we could stretch out the histogram, as shown here, so that it covers the full brightness value range, we would have an image with much better contrast, as we will now see. To do that, we introduce a graph called a brightness value mapping function. It shows us how to take the old brightness values in a histogram and change them to new values which cover the full brightness value range. Effectively, what it does is tell us how to relocate the bars in the histogram more favourably. We usually work out the nature of the brightness value mapping function by examining the recorded histogram and noting the desired new histogram distribution. Once we have that mapping function, we apply it to the image in the following manner. We start with the first pixel in the image, read its value onto the abscissa of the mapping function, and read off its new value from the ordinate. That new value is used in place of the old brightness value of the pixel. That is done pixel by pixel and line by line until all of the pixels in the image have had their brightness values modified according to the brightness value mapping function. The resulting image then makes a much better use of the available range of brightnesses. We have to do that for each band of data. The brightness value mapping function will be different in each case. Here we see the results. Commencing with the poorly contrasting original image, we construct the histogram for each band, then expand those histograms via their own respective brightness value mapping functions. When applied to the pixels in each band, the colour composite image so generated is the much nicer looking image product on the right-hand side. In that final product, we see a much better range of brightness and contrast, and certainly a much better use of colour. You can see now why contrast enhancement is almost always used in remote sensing when visual interpretation is important. Because we are dealing with a discrete number of brightness levels when handling remote sensing imagery, the brightness value mapping functions of the previous slides are actually a set of points equal in number to the number of discrete brightness values. For 8-bit imagery, there will be 256 pairs of input old and output new brightness values. For 10-bit data, there will be 1024 pairs, and so on. As a result, we represent the brightness value mapping function in a computer algorithm as a lookup table, as shown in the last point on this slide. Take particular note of the second question here. The brightness value mapping function does not always need to be linear, as discussed in this lecture. Instead, it can have a range of nonlinear forms which can give added emphasis to particular ranges of brightness.